We now have an infinite series. In this video, we're going to talk specifically about why an infinite series can only be geometric and why it cannot fit in this block here, arithmetic. What do we remember about arithmetic sequences? Right, an arithmetic sequence has a constant difference d. That is to say, for example, 2, 4, 6, 8, 10, it would go on forever, adding 2 every time, with a constant difference in this equation of 2. This is a linear type. Now, what if we were to have an infinite series? Could we ever calculate the sum of an infinite series? This might not seem obvious to you. You might think that it's impossible to calculate the sum of an infinite series because it will always be infinite. The sum would always just keep getting bigger. But this is not actually the case, as we're about to show you. But in this case here, let's have a look at the graph. If we were to draw this graph 2, 4, 6, 8, etc. on 1, 2, 3, 4, we can see that this graph would go off infinitely to infinity. This is why we say that this is diverging. It will always diverge. And as you will soon learn, you cannot get the sum of an infinite series if it diverges. Right. For every linear arithmetic sequence, it will diverge. Now we have a quadratic sequence where the second difference is bigger. This too will diverge. What if we were to draw this? 4, 8, we add 14 here. This will start looking something like this. Starting at 4 at 1, it will look something like this. We're at 4, we have 3. And this starts to look like a quadratic graph that you might recognize. Again, this quadratic graph will keep diverging, as in to say, it is going to keep going to infinity. It is always going to go up to infinity. For an arithmetic sequence, we cannot have a converging graph. It will always get bigger. Therefore, we cannot get the sum of an infinite series for anything arithmetic. But what about a geometric series? We remember a geometric series has a constant ratio. What if we took this example where we're timesing it by 2 every single time? So when 2 times 2 is 4, times 2 is 8, times 8 is 16, etc. What would this look like on a graph? So let's draw this here. We have 2, we doubled it, there's 4, we doubled it again, there's 8, we double it again, there's 16. Ooh. And this would be for 1, 2, n is 1, n is 2, n is 3, n is 4. So what is happening here? It's getting bigger. It starts off here, goes there, goes there. Oh, we can see this is getting bigger. This ratio is increasing as well. This here is a geometric with a constant ratio. The ratio in this case is equal to 2. This is diverging. Why? R, the ratio, is equal to 2. We're going to learn about this later. But basically, if R is either less than 1 or bigger than -1, it will converge. If it is on either side of the scale, greater than 1 or less than -1, it will diverge. What if we had a look at this? Every time we're halving this equation. So 1, we halve it as a half. We halve it again, it's a quarter. We halve it again, it's an eighth. We halve it again, it's 16. What if we were to draw a graph like this? This graph is not going to work very well here, specifically because we've said that that is 16. But this graph would basically always be coming closer and closer and closer to the axes. No matter how much we kept halving it, it would go 1 over 32, 1 over 64. It would never ever get to 0. But what we say is it's converging to 0. That is to say that R, which is equal in this case to a half, because we're halving it every time, and that is creating this converging geometric series. Now we can get a sum, but we'll get into that further. This is basically the equation that we're going to use, and this is for the sum of an infinite series.